Okay, good afternoon, everyone. So today we will discuss this topic, fluid flow equations. So this topic tackles on the different equations, especially in the conservation of mass, conservation of energy, and conservation of momentum applied in the flowing liquid and in a pipe or in an open channel. So, so far, uh, we have discussed the flow of water. We tackled that already in previous topics. But so far, uh, we have discussed the flow of water in hydraulics, and it is governed by the conduit geometry, fluid properties, and some constraints, the external and internal constraints. So for conduit geometry, uh, its characteristic comprised of area, weighted perimeter, hydraulic radius, and roughness of boundaries. So we will discuss that. We will discuss those things further, the weighted perimeter, hydraulic radius, especially when we will discuss the open channels later on in this course. So we also have tackled the fluid properties. It includes the density, viscosity, pressure, and compressibility of fluid. We have discussed that one already. One of the first topics in this course. And we have some constraints. We have some external and internal constraints. So external constraints, actually common to all physical phenomena, are the laws of conservation of mass, energy, and momentum. Yeah, actually, those are the things that we will discuss in these topics. The another constraints, the internal constraints, is the process encompasses the entropy increase law and the space mass time dimensional law and constitute the internal mechanics of the hydraulic system. Actually, we will discuss more of that internal constraints as we go on in our uh, later topics. The term entropy is used to describe the disorder of the system. I think you have heard this one already. The entropy. I don't know if you're familiar with hydrodynamics course. That is the foundation course when you for students taking up mechanical engineering. So manay kuan that's their bread and butter, the hydrodynamics. So for a closed system, the entropy always tends to increase. So in thermodynamics, entropy is usually defined in terms of the irreversible component of heat. So actually, it also occurs in the flow of fluid or flow of liquid in our application in hydraulics. So for a fluid to maintain its flow, it has to perform work to overcome frictional forces resisting flow. So we know that pressure exists everywhere. So for that particular fluid, or that, for example, for that particular water to flow in the pipe, um, it must overcome the frictional force resisting the flow. So this involves irreversible conversion of the flow of energy into heat energy through friction. So we will discuss friction, how to determine friction later in our discussion. Actually, it's on the next topic. So far in our discussion in flow of fluid in a conduit, we'll just neglect friction in order to simplify our discussion. So the increase in entropy in hydraulic system usually occurs due to the conversion of flow energy into heat through friction. So the heat energy is conducted through the fluid and its boundary walls, if any, into the atmosphere and eventually dispersed through space. Okay, so the amount of energy so deployed is a function of the flow, system geometry, and the types of forces and energy affecting the system. The quantitative formulation of this function can be called the process equation, which leads to the resistance equation in hydraulics. Yes, we will discuss this one later. The different components resisting the flow in hydraulics. It is very important when uh, designing water flowing in a pipe or in an open channel. So it can be concluded that every flow process is a conservation process. So yeah, conservation of energy, conservation of mass, and conservation of momentum applies. So because the flow process operates in the universe, which is a continuum of space and time, the process equation must be expressible in space and mass and time dimension. So yeah, in order uh, for the flow, or in order uh, for us to apply those uh, conservation concepts, the flow must be continuous. Okay? So, dili siya putol. So, the equation of continuity, energy, and momentum constitute the basic tools to address the flow problems. It is therefore important to recall their underlying assumption and subsequent limitations. Actually, that mo na atong i-discuss in the next slides. So, first, uh, as I've said, in order for us to apply those conservation of mass, energy, and momentum, the flow must first be continuous. So I think we have discussed this one already, the continuity equation. So for a fluid flowing or traversing on a certain conduit, so it must be continuous. Let's say fluid flowing through point 1 to point 2. If there is no um, leakage, or if there's no input or output, inlet or outlet in between point 1 and 2, so we can say that the Q, or the discharge from that point 1 to that point 2, is just equal. And in our previous discussion, we know that Q, or the discharge, is equal to area times velocity. The area is the cross-sectional area of the flow, and the V is the velocity, or the average velocity of the flow. Okay, so A times B. So A times V. So if Q is constant, so we can say that Q at point 1 is equal to Q at point 2. So A1 V1 is equal to A2 V2. Okay, so that's the uh, basic equation for continuity. You can refer to our book. You can check some explanations and derivations of those equations. Then the next thing that we must consider is the Bernoulli equation. Actually, Bernoulli equation is the popular equation to describe the conservation of energy along the flow. So we have discussed that one already before, the different types of energy occurred in a flow. So we have the kinetic energy, the energy due to the velocity, that's the kinetic energy, and the energy the potential energy that is due to the pressure and its position, or its uh, especially its vertical position. So we can say that the total energy at any point of the fluid traversing through a conduit is just the sum of those energy. So the sum of potential and kinetic energy, uh, sum of pressure energy. So we have also discussed that one in our previous discussion. We can express energy in terms of um, unit unit weight of the liquid. So in such a way that we can express pressure over gamma, or in that case, in that equation, pressure over rho times G. We know that rho times G is equal to gamma. So pressure P over gamma plus alpha times V squared over 2G. Actually, alpha is just the uh, energy, kinetic energy correction factor. So it's actually a coefficient, but in most application, in most cases, alpha is just equal to 1. So that we can cancel out alpha as 1, or we can let that as 1. So times 1, eventually mawala na siya sa equation. So V squared over 2G, that's the kinetic energy, plus the Z, or the energy due to its vertical position, the potential energy. So in that case, if we are to examine, if we are to determine the total energy of the fluid possessed at point 1, so at A1, for example, so the total energy is uh, energy due to pressure, is the pressure of the water inside, or pressure of the fluid inside the pipe, and energy of the velocity, because it is flowing, so it has a kinetic energy, so it has energy due to velocity, and the energy due to its position. So its position is a certain distance, a vertical distance from a certain datum. Okay, so that's the total energy. P over gamma, V squared over 2G, plus the Z, its elevation. Okay, so yes, we can, based on those things, we can have some examples. So water flows steadily through a horizontal nozzle. So this is our nozzle. So it is positioned as horizontal, so that if we will let this as our point 1, and this one is our point 2, so point 1 and point 2 have the same elevation. So if they have the same elevation, so they're lying on, of course, they're lying on horizontally. So their difference in elevation is just equal to 0. They're lying on the same plane, man. Okay, so the nozzle inlet has a diameter of 6 inches. So this is our inlet, point 1. Yeah, this is our point 1. And this is our outlet at point 2. Sorry, here, point 2. So the nozzle outlet, uh, at the nozzle outlet, the pressure is at atmospheric. So mao man ni siya ang nozzle, so ari mo gawas ang atong flow at point 2. So we can just assume, since gawas naman ni siya, padung naman ni gawas, you can just assume that the pressure at point 2 is equal to atmospheric pressure. So what does that mean? If the pressure is equal to atmospheric pressure, it means that the gauge pressure is equal to 0. So its diameter is 2 inches. The question is, we need to determine the pressure head at the nozzle inlet required to produce a velocity of 40 feet per second. So I think ang velocity nga iyang gimean ani dire, I think the velocity iyang gimean is the velocity of the flowing water. The problem does not specify um, what velocity at point 1 or point 2. Basta ang iyang ipangutana is we have to determine the pressure head at the inlet. How much is the pressure or pressure head at point 1? So we have to neglect friction between point 1 and point 2. So although sa actual nana siya friction loss, known as a head loss. But for this discussion, we can just neglect it. We'll just discuss it later. Okay. So solution. So first, we need to determine the area, the area of the mm, based on the given diameter. I think I'll try to solve the area. I try to check ano 5 man nga ang given is 6 and 2 man. I'll try to check ha. Okay, yeah, sakto day. The area is the problem considering the area is we will solve first the area at point 1. So the area at point 1 is equal to pi d squared over 4. So it's point 0.5 actually this is point 0.5 feet because it's 6 inches. Okay, so 6 inches is equal to point 0.5 feet. So the area is equal to 0.196 feet. Okay, so that's 0.196 square foot. Square foot. So we will also solve the area at point 0.2. So 2 inches. So that's equal to 2 divided by 12 and square times 5. So that is equal to 0.021, 0.0218 square foot. Yeah, 0.0218 square foot. So we can apply the continuity equation at point 1 and point 2. So we can solve for the velocity, or we can express V1 in terms of A2 V2 over A1. Okay, so in that way, we can solve for V1. This is the area, this is the A2. Then this is the V2. Okay, so this is the V2. V2 is given. It's 40 feet per 40 feet per second. That is the diameter of the water exiting the nozzle. So substituting that to the continuity equation, we can solve V1 as A2. This is A2.018 feet square foot times V2 divided by A1. So we can solve for the velocity of V1 as 4.44 feet per second. The question is we need to determine the pressure head at the nozzle inlet. So pressure head at point 1. So we can apply the Bernoulli's energy equation. So it is stated in the problem that there is no energy loss between point 1 and point 2. So we can say that energy at point 1 is just equal to energy at point 2. So total energy at point 1 is 1. Mao ni siya. Z1, pressure 1, V1 is equal to Z2, pressure 2, and V2. So eventually, gamma is equal to rho over G. That is equal to the specific weight of the water, which is equal to 62.4. That is equal to um, 1,000 kilograms per cubic meter. And we know that Z1 and Z2 has the same value, so we can just cancel Z1 and Z2. They are the same and they're found on both sides of the equation, so we can just cancel them out. So we can rearrange the equation. This one, this um, this one, ako na lang ni ang nabilin. Okay, na-cancel out ang Z1 and Z2. So, mao na lang ni ang remain sa atong equation. So, we can rearrange these two, so that we can get the pressure head. P1, okay ha, basin maglibog mo. P1 is the pressure, okay? P1 is the pressure and P1 over gamma is the pressure head. This one, muna siya ang this is the actually the pressure head. Kanang entire thing, P1 over gamma. P1, balik ko na ko, P1 is the pressure, P1 over gamma is the pressure head. So we can solve for pressure head by rearranging this equation, this one. So we can solve for pressure head. Since it is a head, pressure head, so that is 24.54. If we're going to solve for the pressure, so we'll just multiply the pressure to its unit weight. I mean, we just multiply the pressure head, it's 24.4 times 62.4. So the pressure is equal to 1531 psi. Or 1531 pound per square foot. Square foot pa man na siya. If we will to convert that into pounds per square inches, ato na siyang i-divided by 12 squared. Okay? So, I think example number 2. So, example number 2, we have a pipe that has a length of 300 meters. It has a slope of 1:100, and it conveys, I don't know if it's water. Water. Yeah, it conveys water at 5,400 liters per minute. Okay, that's the Q. That's the discharge. Discharge of the water is 5,400 liters per minute, and the diameter of pipe, let's say at 0.1, based on the figure, is 0.5 meter, and at 0.2, ang nasa mabaw at the upper part, at the upper portion, is 1 meter. Remember that we have a slope of 1:100, so that the change in elevation of the pipe is equal to length times the slope, 300 times 1/100. So we have difference in elevation between 0.1 and 0.2 equal to 3 meters. So 0.2 is higher than 3 meters compared to 0.1. Okay, so assume the energy loss due to friction inside the pipe is negligible. So we don't consider any friction loss between point 1 and point 2. So first, we need to solve the Q. So you know already how to convert 5,400 liters per minute is equal to 0.09 cubic meters per second. Then by that, we can solve for the V1, the velocity at point 1, Q over area. So 0.09 over area. So the velocity at point 1 is equal to 0.46 meters per second. So velocity at point 2 is equal to 0.115 meters per second. Then applying the Bernoulli's energy equation or Bernoulli's equation, we can equate the total energy at point 1 and point 2 since we don't have any energy loss between point 1 and point 2. So we can just put point 1 and point 2 directly opposite of the equation. So pressure head, that's the pressure head. That's the velocity head. Then that's the elevation head. Okay, so for point 1, pressure head at point 1, we do not know. Wala ta kabalo. At point 2, velocity head, yeah, we already solved that one over 2g. Elevation at point 1 is, we assume it as 0. And pressure at point 2, I think this is given, 6.87. I think this is given in the problem. Yeah, the pressure at point 2 is equal to 68.7 kilopascal. Okay, 68.7 kilopascal. That's the pressure at no, this is, I think, sa maning problem. 1 meter diameter at its upper end where the pressure is, yeah, the pressure at upper end is 68.7 kilopascal. So we need to determine the pressure at point 1. So we don't know this one, the pressure head or the pressure at point 1. So pressure at point 2 is given as 68.7 kilopascal. So this is the pressure head. This is the velocity head. That's the velocity 0.115 square over 2g. Then this is the elevation head at point 2, which is 3 meters. Okay. So the only unknown in the equation is P1. We know that gamma is equal to 1,000, or in this case, gamma naman siya. So this is 9.8 kilonewton per cubic meter. So the only unknown in the equation is the pressure. For pressure head, so that's 9.99 meters. So because this is a head, pressure over gamma, it's a head, 9.99 meters. For the pressure, we can just multiply it as kining 9.99. We can just multiply it to 9.8 kilonewton per cubic meter. So that's 98 kilonewton per square meter. So that's 98 kilopascal. So it should be noted that since the energy loss due to friction is neglected, the flow direction, either upward or downward, would not affect the result. Yeah, because there is no friction man between point 1 and point 2. So, is there any question? Yeah, nahata example na number 3. Example number 3. So, we have an open channel. The previous 2 examples are in pipes. So, for example number 3, we have an open channel. So the difference between pipes and open channel is, for the open channel, we can assume the pressure is equal to atmospheric pressure. So we can say that the gauge pressure is equal to 0. By the way, for previous examples, the pressure involved or the pressure mentioned in those problem are all gauge pressure. They are not atmospheric pressure. They are gauge pressure. Okay. So example number 3, we have water discharges over a spillway. So a spillway, so it's kind of a dam. It's kind of a structure that is used to impound water. Uh, Dam, it's the one of the dam designs that is designed uh, designed in such a way that it is normal for the water to overflow. So it's a spillway. So like spillway shown in the figure, the depth behind the spillway is 24 feet, and the spillway and the downstream channel are both 50 feet wide. So yeah, it has a width of 50 feet, so lapad kay siya, and the depth at the two of the spillway is 0.41 feet. So mo ni siya point 41 ni apaw siya, then the depth diri sa likod is 0.41. So assuming that the velocity behind the spillway is very small, such as the velocity head can be neglected. So very small ko ang velocity, it can be neglected, and ignoring the friction losses on the spillway face. So as the water flows through this spillway, because this material has its roughness, so in the actual it must have velocity. I mean friction loss. It must have a friction, so it must have a energy loss. But this, as I've said, for simplicity of this topic, we'll just ignore the friction losses. Actually, in the next topic, we won't ignore the dili na nato i-ignore ang friction kay mao man na basically ang ato topic is about friction flow in a pipe. So for these examples, for this discussion, we'll just ignore the friction occur from between points of consideration. So pangutana is, what is the discharge over the spillway? Pila ko na discharge? Pila ko na discharge sa water nga ni ni flow on the top of the spillway. Okay, so we can just apply directly the Bernoulli's energy equation. So okay, this is point 1 or upstream. This is the upstream. This is the total energy upstream. Then this is the total energy downstream. So akong i-explain. So nganong 24 naman lang ni siya. Okay, so we know that the energy involved are velocity, pressure, and elevation. So if we will consider this as our point 1, this portion here, this is our point 1, then this is our point 2, diri nga portion, diri nga portion. We can say that at this point, pressure is equal to atmospheric pressure. So pressure is equal to, or gauge pressure is equal to 0. So wala na ang pressure, 0 na siya. And we know that at this portion here, we can just neglect the velocity because this is our reservoir. Marami siya og reservoir, more like storage. So its relative velocity can be neglected. Although na siya velocity, but it's very, very small compared to velocities involved. So we can just neglect the velocity at, let's say, at point 1. Okay? So 0 ang velocity, 0 ang pressure. That's why what remains is only the elevation head, which is 24. Okay, so we consider this one as our datum. Okay, so that is 4.1. 4.2, yeah, naaday ko'y sipyat kanina. I think nasayo ko pag-interpret sa problem. Ang pasabot niya, the problem behind the spillway is actually 0.1. This is the behind the spillway. So velocity ko no at this area at this point is very small. At diri ay mo din ang front sa spillway iyang gipasabot. I think na kuan sa orientation murag na kuan ang problem. We can neglect the velocity here. So sakto to atong assumption diri dai sa likod. We cannot neglect the velocity because this is actually where we will solve the velocity kini nga portion na ani siya velocity. Ang diri ay balikon ako diri ay nga portion mo ay walay velocity. So that at point 2, so this is our point 1 on the behind the spillway on the left side of the spillway. This is our point 2 diri nga side. So at point 2, of course, this is exposed to atmospheric pressure, so gauge pressure is equal to 0. So pressure niya is 0 na la. What remains is the velocity head and the elevation head. So that's why this is our elevation head, which is 0.41 feet, and this is our velocity head. So what remains in the equation, what is unknown in the equation is just the velocity. So we can solve for the velocity. So 24 minus 0.41 times 2 times g, that's 32.2. So the velocity is equal to 38.98 feet per second. So if we already have the velocity, we can just solve the area, cross-sectional area. Cross-sectional area, it's 0.41, that's the height of the water, times the width of the spillway, that is 50 feet. So times 38.98, that's roughly 799 cubic foot per second. Okay? So if you have a question, you can just type your question in the comments. Okay. So that's it for examples in the involving continuity equation and Bernoulli's energy equation. So we have here the limitation of Bernoulli's energy equation or Bernoulli's equation. So in almost all problems or almost all equation, there must be a limitation and some validity. So we have limitations because when we derive the equations, or if you'll read our book, you can see the derivation of the Bernoulli's equation. During the derivation, there are some what we call assumptions. So those assumptions create or because of those assumptions, there are what we call the limitation and the applicability, also the validity of this equation. So first, this equation, Bernoulli's equation, is applicable only uh, is applicable only in steady state problems, steady care, steady state problem. Steady state problem. So meaning steady state problem, it means that the velocity is constant all throughout, or velocity, or the velocity is steady or steady flow. So dili na siya pwede og unsteady flow. Okay. So mana yung mga limit. So that's why in an open channel, sometimes we don't use na the Bernoulli's energy equation, especially in advanced hydraulics, advanced problems. So if the flow is unsteady, we cannot apply Bernoulli's energy equation. We can still use the principle, but we cannot apply algebraic solution. Bernoulli's energy equation is kuan man ni siya. We can solve it in analytical method, algebraic method. Mogamit kung unsteady problems, mogamit sa calculus. Kaya na naman siya rate of change. So magamit na ta og differential equations. In many practical applications, there are some losses of energy. Mag-away naman po ning mag-away ning mga tao there is silingan. Anyway, yan na ang problem. So, in many practical applications, there are some losses of energy. So, man akong mention kanina, we'll just neglect energy loss. So, there's some losses of energy due to frictional forces exerted between the flowing fluid and the conduit of the flow. And also in turbulent flow, some kinetic energy is converted into heat energy. While in viscous flow, so you're familiar, you know that one, viscous fluid. Viscous fluid, example ana, like concrete, it's a viscous fluid. Flow of heavy oil, so that's a viscous fluid. In viscous flow, some energy is lost to overcome shear stress. Yeah, dagko kay na siya shear stress. So such losses should be integrated into the equation. So actually, mo na ganina, if you're familiar with katong flow correction factor, tong alpha. So mana siya. But in flow of water, good for practical application, we'll just let it as 1 kanang coefficient. Another is the velocity of every particle of the fluid is assumed constant across any section of the hydraulic conduit. So yeah, velocity is assumed constant. Of course, di siya constant if dili the same ang iyang cross section, but if same ang iyang cross section, we will assume it as constant. But in reality, that's not the case. Maglahi-lahi man na iyang velocity. So the Bernoulli's equation does not account for velocity variation in the lateral direction through the cross-section of the flow. So ato ra sa siyang gi-assume nga it's a one-dimensional flow. Okay, so in reality, naman na siya ang velocity, ang water particle, di man na siya straight flow, magbabag-babag man na siya. So naman na siya lateral direction. So wala na gi-consider sa one. I emphasize this one so that you will know there are limitations sa this equation. Before God, when I was still in college, dito raw discuss ang maestra. So I thought nga this equation can be applicable to all. Then later on, I realized when I took up advanced hydraulics, although we can as I've said, we can apply the same concept, we can apply the same principles, but we cannot use the original equations. So kuan na siya, puro na siya partial differential equation. Okay, so another is the gravity. The gravity force is considered only to be the external force acting on the flowing fluid. This is not always true in many application, in many problems where friction force as well as other external forces affects the flow pattern considerably. Centrifugal force due to curve paths are not considered. Okay, so kung yung mga curves nga ko naman na siya because it has a change in momentum, so na siya ay centrifugal forces, so wala na gi-consider sa energy, sa Bernoulli equation. The Bernoulli equation is not applicable through propeller machines. The equation was derived by integrating along a stream of tubes. So if you can see in the book, there's a derivation. It's gidrive ra na siya on a smooth stream, so from point 1 to point 2, in the absence of a moving surface such as veins in between. So however, it may be applied before and after the machines. So mo na nga later on in our examples, mag-solve ta og mga pumps. Ato nang i-separately solve ang pumps or ang energy loss due to that particular pump. We can apply the Bernoulli equation before and after the turbine or a pump. Okay. So in such cases, the energy loss inside this machine should be considered. Yeah, nanay discussion ana later on. So aside from Bernoulli, ang Bernoulli is all about conservation of energy, di ba? We mentioned about energy from point 1 to point 2. So another thing to consider is the momentum equation. So going back to the Newton's second law of motion, the rate of change of momentum is proportional to the applied force and takes place in the direction in which the force acts. Okay, so ang rate of change ko no of particular momentum in moving or not moving object is proportional to the actually the force is proportional, or the applied force is proportional to the change in momentum. It is also proportional to the mass and the acceleration of the body. Okay, so if na kay change in direction or change in velocity, so you have a change of momentum, di ba? I think you know that one in your physics. Change in velocity or change in direction, so you have a change in momentum. Okay, so mathematically, it can be expressed with that equation, first equation, this one, F is equal to mass over, actually that's mass, velocity over dt. Mass, constant man na siya ang mass, di ba? So, ang ma-change is ang velocity. So, dv, actually it's dv over dt. So, we know that dv over dt is rate of change of the velocity with respect to time. So that's what we call the acceleration. So we know that force is equal to mass times acceleration. So if we will apply that concept in a moving fluid, okay, we will apply that one. So we can apply that one, diba? In a moving fluid, we have discharge. So when we say discharge, we have unit time, diba? Cubic per, or pwede mo siya og mass discharge or volume discharge. So in terms of volume or in terms of mass, so pwede kilograms per second or liters per second. So the common is naata unit of time. So if we will slice that unit of time into what we call the delta t, okay, change of time delta t. So yeah, we can apply to that. We can apply that this equation kini ma-apply na to na sa flowing liquid. So force or delta force is equal to rho density. Basically ang density, if we will assume that the fluid is incompressible, so we can say that the density all throughout the flow is the same, di ba? So same naman kung incompressible, but in most application is we can just assume it as incompressible. So rho is just constant, so wala na siya labot. So delta Q times delta T. So we know that V2 over V1 over delta T is equal to acceleration, di ba? So in this equation, we can just cancel delta T, di ba? So what remains is rho delta Q V2 over V1. Actually, kining V2 over V1 is mao man ni siya ang change in velocity. Di ba? Mao man na sa atong physics, change in velocity na acceleration. Okay, so V1 and V2. Change of velocity or change of its direction. So this is the equation. Delta Q V2 V1 times rho. Okay. So if delta F man siya. If we will integrate this one, integral, so mawala ni siya actually ang rate of change sa Q, mawala ang rate of change sa F, so mawala ang delta. Ato na siyang integrate. So mahimo na siyang F rho Q V2 and V1. So in many applications, so namagod tayo X and Y component. So we'll just break it in this component. So if along X, mana siya, V, since F and V are vector quantities, so nana siya subscript nga X or Y. So if the direction of the force is along X, so that equation, if along Y, so Fy, so velocity is along Y, so Vy, V2y, V1y. Okay. So I think we have an example. So, okay, we need to calculate the magnitude and the direction of the force exerted by the horizontal pipe bend. So, nakuno kay pipe bend, we need to calculate the magnitude and direction of the force exerted, as shown in the figure. If the diameter is 20 cm, I think same ra ni siya diameter kay mao ra man ni siya nga pipe all throughout. And the upstream pressure head at the centroid is 5 meters. So pressure head ko no, upstream is 5 meters. I think upstream is mo na siya ang 2 siguro 0.2. Yung pressure head is 5 meters. So take note ha, pressure head, it's 5 meters. If we need to convert that into pressure, we'll just multiply that head 5 meters by gamma. So we know it's pressure. And the discharge all throughout 0.1 and 0.2 all throughout the pipe, since the pipe is since the pipe has the same diameter, so we can say that this discharge is constant all throughout as 0.2 cubic meters per second. Okay, so since the diameter of the pipe does not vary, so constant ra ang iyang flow, which is 0.2 cubic meters per second. So yeah, mo na siya ang equation. F along X and along Y, so V along X and along Y. So rho Q man na siya. Q is the discharge, rho is the density. We can also rewrite Q as gamma over G, because we know that gamma is equal to rho times G, diba? So we can replace rho as gamma over G. Okay. So the velocity through the bend is constant, and yeah, we can solve for the velocity Q over area. So velocity is 6.366 meters per second. So since the bend is horizontal ba ni siya? Yeah, horizontal 5. So kuan din ni siya, top view. Okay, top view. Since top view ni siya, ang upstream depende, the upstream man god depends on the direction of the flow. So horizontal, so the static heads at the inlet and outlet must be the same. So yeah, same ra siya. Pressure head at 0.1 is equal to pressure head at pressure head 0.1 is equal to pressure head at 0.2, which is equal to 5 meters. So we can solve for the pressure. 9.81, yeah, that's 5 times 9,810. So that's 49050 Pascal Newton per square meter. So the pressure force, naman tay pressure, so we can solve for the force. Actually, kana nga force that is due to the static pressure. Wala pa nilabot ang momentum. Okay, so patay force equal to pressure times area. Okay, so force is equal to pressure 49050 times area. Of course, area of the pipe. Okay, the diameter is 20 cm. So times area. So naatay force due to pressure nga 1540 Newton. Actually, kining 1540, if you can observe naatay plus and minus, the positive and negative sign refers in this particular in his particular topic, the positive and negative sign refers to the direction, because vector is practically important in this topic. Vector vector based man eh. So positive and negative is just equal to, or is equal to, or positive and negative referring to the direction of the force. So force along x, that's 1540 Newton. I think ang kana nga x, I mean kanang positive is going to the right. I think that's the assumption of the book. The force is going to the right, that's positive. Going to the left, that's negative. Going upward, that's positive. Going downward, that's negative. Okay? So along y, negative siya. P2, so negative, it indicates going downward. So mao to siya before ang force due to pressure. Kini siyang sunod nga calculation is this is now due to the momentum. This is now due to the movement. So tari na ma-apply ang equation nga rho q times b2 over b1. So we need to solve the forces based on its component x and y. So along x, V2 minus V1. So, positive actually ang V1 but minus man ang iyang sign daan. So, the rho, 1,000. The discharge, 0.2. Velocity is 6.366. Okay? Minus. So, that's minus 1273. Isin mahibong mo ha? Nganong minus 6366? As I've said, positive ang velocity but you can if you recall, ang equation is minus man. Kung negative man atong velocity, so ma-plus na siya kay minus negative pa jud. But since positive man ang atong velocity, so manang negative siya. Okay? Kay minus man ni daan. For y, so for y, v2, 0 ang iyang V1, ang iyang V2 is same raman siya og positive gihapon, so 1273. So going to the left, then going upward. So we can solve for its resultant. So ato raman ni siyang i-add ang due to pressure and due to change in momentum. So unang 1540, actually negative 1540 plus negative 1276, so that's negative 213. And ang kinisad siya sa y, positive man sila tanan, so 1540, positive 1540 plus positive 1273, so 2813. So nanatay components x and y, so we can just solve for its resultant. Then the direction, same naman sila og value, so that's 45 degrees. Actually, it is expected nga 45 degrees. Actually, the direction of the force is the direction of the force is saan man to? Remember that x is negative, y is positive, so na siya. Ano siya ang resultant. So that's 45 degrees. Okay. So another example. So ganina, it's on a pipe, closed pipe, or inside the pipe. Kini nga example is in an open surface. So we have a jet of water. It's being deflected 60 degrees by a frictionless vane. So this is the vane. Mani siya ang vane. Then you have a jet of water. You have a water flowing in that direction. The velocity of that jet of water is 40 feet per second. Okay, that's 40 feet per second. And the vane is moving at 6 feet per second. Okay, so you have to determine the force exerted by the jet on the vane. So since the vane is moving, ganina at example is the pipe joint, wa man to siya nag-move. Ang vane na to is moving man, so the jet is also moving, so we need to determine its relative velocity. The relative velocity is the net velocity between the flowing jet and the moving object, or the moving water and the moving object. First, we need to solve for its relative velocity. So that's 40 minus 6, that's 34 feet per second. So applying the equation, rho times q, velocity. Remember that the vane is has an angle of 60 degrees. So na kay angle nga 60 degrees. So ang atong V1 is horizontal ang iyang velocity, di ba? That's the horizontal velocity. Ang atong V2 is dili na siya horizontal. So nakalinya siya 60 degrees above siya upward. Okay, so we have V component, the exiting velocity, na natay y component and x component. At the bottom, it's only x component 0 ang atong y component. So that when applying those velocity at the equation, so kay yan kay q. The q is 34 times mo ni siya ang q. 34 times the area in 018. Okay, then the velocity is V2 along x ni siya. Ang atong component is now 34 cosine 60. So going to the right, 34 cosine 60. That's our V2. Ang atong V1 is 34. Okay, horizontal man siya. So the answer is 24.5 pounds. For Y, for By, of course, this is the rho. This is the rho. This is the Q. Ang Vy na to, ang atong V2 is 34 sine 60. That's positive going upward, di ba? 34 sine 60, that's the component. Importante siya kay mamagunay tendency bisin malipat mo ba. 34 sine 60, that's the y component. Positive or plus because it's going upward. Ang iyang V1 is 0. Okay, wala may y component ang V1 because it's horizontal. So y component of the force, acting force, that's 42.34. Okay? So The resultant force is 48.9 and the angle of action is negative 60. Actually, negative 60 kay ana man na siya. Ang atong application sa force it's ana man na negative 60 paana. Actually, it's 60 degrees from the horizontal. Diba? Dire nga horizontal. That's negative 60. Actually, it's perpendicular to the direction of the vane. It's perpendicular kay 60 upward man siya 60 degrees then kini siya downward 60 degrees. Okay? So any questions so far? So that would be all for our discussion in fluid flow equations. If you have questions or clarifications, you can just chat it in MS Teams. You can just write it in the comments in this post. Okay, so that would be all for this discussion. Thank you for your attention.